Hello, everybody. My name is Dr. John Freem. I'm the Director of Material Science at Regenesis. And the webinar I'm going to be presenting about today is going to talk about using a combination of colloidal activated carbon and zero valent iron to accomplish the in-situ remediation of chlorinated contaminants. So let's talk about the first part of our mixture here, which is colloidal activated carbon. And what is this? Well, most of you probably know what powdered activated carbon is. It's derived from coconut shells or possibly coal. And the feature that's enabling with PAC is that it's got a very, very porous microstructure. It's got an open porosity of about 500 meters squared per gram. Because of that, it's a very effective sorbent for chlorinated compounds and many other groundwater contaminants. But the problem with this is it's got a relatively large particle size. You can vary anywhere from a millimeter down to about 30 microns. And the problem with this is the particle size that get above, say, 10 microns, somewhere around there, it's relatively difficult to place into the ground using your standard injection techniques. So realizing this problem at Regenesis, is we've developed techniques to process PAC particles into much smaller colloidal suspensions that have activated carbons with about 1.5 micron diameter particles. This is done via advanced grinding techniques, and the key feature of this process is that we use organic polymers to promote stable dispersions and improve the transport properties of the material at low pressures. So it's a great sorbent that can be placed widely in the ground, but one thing that we need to realize is that active carbonating does not directly promote degradation. So let's see what happens if we do a barrier in the ground with activated carbon alone. We have a model called plume force, and here you can see the assumptions: seepage velocity of a couple hundred feet per year, mixture of parents and daughters, 7-time runtime with no degradation, no biodegradation, no abiotic degradation. So here's the plot. You can see the on the left is the incoming or the up gradient concentrations of the contaminants. We have about 1,000 micrograms per liter of PCE and subsequently lesser amounts of the daughters. And the gray box in the middle there represents our barrier. So the contaminants are flowing with the groundwater, they reach the barrier, and then they emerge on the other side of it. What you can see is that PCE towards the back of the barrier does get fully absorbed, and there's nothing coming out the back end because PCE is more hydrophobic, it absorbs better. So it's going to basically occupy all or nearly all of the activated carbon absorption sites. But the daughter products, there's not really enough surface area or absorption capacity on the carbon in the wall to absorb these, so they break through. And the orange line is TCE, and you go down, you can see cis and vinyl. Basically, the effluent coming out the barrier is the same as it is coming in, and there's no degradation products. In this case, would be ethene or ethane. So we realized that you need to have a combination of absorption, which is done by the activated carbon, by the plume stop, with a reductive degradation mechanism. And there's two general classifications where we can accomplish this. One of them is called abiotic or chemical reduction, sometimes referred to as ISCR. And there's a couple ways that this can be done. One is you can use ZVI, the powerful reductant, reacts directly with PCE and other chlorinated compounds, and produces a mixture of ethene and ethane, but largely ethane. And we can call this direct abiotic reduction. There's also indirect methods, which are biogeochemical. When you have native sulfate in the water producing conditions, you can form reduced iron sulfides and other reduced reactive minerals in situ that can also accomplish reduction by ISCR. Not as powerful as ZVI alone, but it does work. The other side of the equation will be biological reduction, which a lot of people probably are more familiar with. That's where you combine your contaminants such as PCE with molecular hydrogen produced generally by the degradation of organic compounds, nutrients, anaerobic microbes, which could be either native or augmented, and you'll generally get the final product of ethene through daughters. So PCE will do its cascade through TCE, cis-TCE, and vinyl chloride. So what do we want to use? And we have a choice of biological or abiotic degradation. And we can walk through the features of each of these methods and give you an idea of what works best and the limitations of each method. So biological products, either water soluble, such as sodium lactate, or emulsions, such as EBO or 3-DME, very easy to apply and you get good distribution. Basically water-like products. But one thing we need to consider is that some amendments, such as emulsified vegetable oil, can inhibit contaminant absorption onto the carbon. There's actually a competition process, between the contaminants and the vegetable oil particles, and you'll actually probably, in most cases, have higher concentrations of your oil. They'll preferentially absorb to your carbon, blind it, and you're not going to get very good performance. The other thing about biological degradation is that it does produce daughters. So if you have a site with TCE and PCE primarily, you're almost surely going to get a cascade with the daughters. And the thing about these daughters is that they actually don't absorb as well to carbon as the fully chlorinated compounds. And it's relatively slow. In a good environment, it can happen in a time frame of months, probably would be typical. Abiotic degradation with ZVI. We have a colloidal iron product here at Regenesis with a particle size. It's about the same as colloidal carbon, so they can be applied together. Unlike the biological amendments, if you put them in the same mix tank, inject them together, and generally they'll be delivered to the same place in the ground. The thing that's really nice about ZVI, it doesn't inhibit contaminant absorption onto the carbon surfaces. You minimize daughter product formation. You don't eliminate it entirely, but typically we see 90% or so of the parents transform directly to ethene through what's called a beta elimination process. And because it's a solid phase reductant, your persistence. Soluble amendments such as lactate will eventually react away or be passed downstream with groundwater flow. So let's talk about our iron product, or sulfinated iron, S-micro-ZVI. This picture on the left is an artist depiction of what these particles look like. And one thing that's important to realize is that, first of all, they're small. The particle size is about 3 microns. But we engineer it. We take a particle and we electrochemically deposit a reduced iron sulfide surface, FES, which is the yellow phase on this particle, onto the surface of the core, which is iron. So it's called a core shell configuration. And there's a lot of reasons why this is better, but I'll just cut to the chase. When we do tests, and it's not just us at Regenesis, this has been done at universities and other labs. You see kinetics with TCE and PCE on average, probably about 30 times greater than you're going to get with bare ZVI. As is the case with other iron products, as I said earlier, daughter products are minimized, about a 90% or greater directly to ethene. And in the right environment, with the proper dosing, you can get a reactive life of many years. So let's look at our barrier that I talked about earlier, where I showed activated carbon alone. What we've done here is, to our plume force model, we've added 3 grams per liter per volume basis, solid SMZVI particles to the prior design, have the same flow conditions, etc. And you can see that the behavior is quite different. The PCE and the TCE are removed at the front of the barrier, drop down to 0, but you also get removal of your daughter products. They react abiotically, and it takes a little bit longer than they have to pass through more of the barrier to be totally removed. But in this situation, by the time they reach the back, they're fully reacted or absorbed away. And unlike the other process, because we have active degradation, you can see that green line that comes up and we have ethene and ethane produced and generated in the down gradient part of the plume. The fundamentals I'd like to do now is actually show you some examples of where this process was used in real applications. So the first one, I'm going to talk about three here. There's a single barrier where we had a co-injection of plume stop colloidal activated carbon and sulfated colloidal zero valent iron within a barrier. And on top of that, this was done a couple of years ago, so the iron technology was relatively new. We decided to be safe and add some HRC, a long release organic hydrogen produced by Regenesis, and dechlorine microbes. And these were injected slightly up gradient of the barrier that had the carbon in the ion. To monitor this, we had one monitoring well within the barrier. That's the blue dot there in the middle, CMW, and three monitoring wells, which are 15 to 20 feet down gradient. And these are, outside the direct influence of the injection. So any effect you're going to see here is actually the effect of the contaminants being reacted away within the barrier. And you're seeing the effect of the groundwater that's coming through cleaner than when it is going into it. For your reference, the groundwater flow here is perpendicular to the barrier or from the upper left to the lower right. So this is the response that we saw within the barrier, which is CMW3, the blue dot that was right in the middle of the injection. And as you'd expect, we have direct influence here. This monitoring well had black material, which is the carbon and the iron within the water. And in the first monitoring period, we saw the full elimination of all the compounds, which, is not that surprising. A lot of that's probably due to absorption. But what we like to do is look for degradation products, to look for evidence that we're actually seeing active degradation. As I premised this earlier, we don't want only absorption. We want to absorb, then we want to degrade, free up the surfaces of the carbon, and it's kind of a circle where you can keep the barrier working for a long time. And the evidence that this is happening, the green lines, the lighter green line is concentrations of ethane, and the darker green line is the concentrations of ethene at this monitoring well. And you can see this peaked about 100 days after the injection and continued on for over 400 days. And this very, very strongly suggests that we're actually not just having absorption, but we're having active degradation within the barrier as well. I decided to plot the downgraded barrier slightly differently. First of all, this is a log scale plot. So you can see the concentration on the left is a log scale. And what I've here is not only plotted the concentration of the contaminant at the down gradient monitoring well, but I've also compared them to our plume force model, which assumed only biological degradation. So we plugged in how they behave if we only had the HRC applied and not the iron. So we'll run through these one at a time. The red line there is TCE, and the dashed red line is what. So you can see there's pretty steady degradation after a few days. There's no TCE in the down gradient well, and the degradation process was markedly faster than what we predicted by biological behavior alone, which strongly suggests melodic degradation, which was also verified by the presence of our ethane and ethene in this well. If you look at the daughter products, this well actually had more cis than TCE at the beginning. You see the orangish line on the top is our cis concentration. It started off at about 1,000 micrograms per liter, and it steadily degraded. It's down to maybe 20 micrograms per liter after 400 days. So we had, a 95% degradation or greater, let's say. And generally during the entire process, we had faster degradation than what was predicted by biological models. So we probably had a mixture of abiotic and biological here. Hard to say what was more prevalent. The yellow line is final chloride. Started off at a couple hundred micrograms per liter, and this generally followed, what would be predicted by biological degradation. There's still about 80% removed compared to what was there originally. It doesn't show quite so dramatically since this is a log plot. And these results actually make sense. If you look at kinetics of ZVI with chlorinated compounds, TCE is considerably faster than cis, which is a little bit faster than vinyl. So we're actually seeing the behavior that's pretty close to what we'd expect, and we're going to continue to look at the site moving forward. The second site I'll talk about is carbon and ZVI alone. Instead of a single barrier, we actually have 5 barriers, about 100 feet apart. It's a large project, 158 DPT points from 8 to 30 feet BGS, bottom up, and almost 100,000 pounds of plume stock, 72,000 pounds of aqua ZVI, and 200,000 pounds of injectate, about 60 gallons per linear foot. Pretty substantial program. We had 2 monitoring wells, shallow zone, which was 6 to 20 feet below ground, and the deep zone was 20 to 30 feet below ground. So what I've done here is that when I've summarized these, I've averaged the concentration in the shallow and the deep. For the most part, they really aren't that different. So you see here on the right is a map of the site. The white area there shows the monitoring well down gradient of the first barrier, and we had really good results. We had about a 95% reduction in our parent compounds, 80% reduction in the daughters, the total VOCs, 94% reduction, and the decrease in our compounds was accompanied by an increase of mostly ethane. So we just a little, it's a strong suggest that we're seeing mostly degradation. Down to the gradient barrier, pretty similar, maybe slighter. We had about a 90% reduction in chlorinated compounds, and mixture of ethane and ethane, but probably a little bit more ethane than ethene here. So we'll walk down grade another barrier. Might be a little bit more concentrated down here, 200 microgram meter total VOCs at our initial monitoring period before the injection. And we've had a steady decrease there as well. 5% reduction in both parents and daughters, with mostly ethane produced, indicative of abiotic degradation. And we can walk down to the fourth here, pretty similar, a little bit better reduction in PCE and TC, 96%, but still great reduction, and is continuing. And we get down to the very last barrier. We're seeing a little bit less reduction there, but it's still in the mid to the high 80s. So this is, basically showing that in a barrier configuration, a combination of plume stop and iron is an effective combination. I will say that there was a lot of pre-planning design verification that went to the site using flux meters and plume force model and our ZVI degradation model that we use to plan and this. So as always, when you use Regenesis, you're going to get some of the best technical service in the business that will help you with your design and make sure you try to get things right the first time. So here's the summary here, site-wide, 95% reduction in PCE. That slows down a little bit as we get down to the daughters. Large increases in ethene and ethane. As we expected, the kinetics of the parents is greater than the kinetics of the daughters. That's just an iron reduction. One thing that's nice is that we're not seeing any accumulation of daughters, which is once again expected from iron. And as I said earlier, we've got mostly ethane, indicative of abiotic degradation. I'm sure there's a little biological going on for the ride, but it's not the primary destruction mechanism. So here's the third site. It's depicted here. The barrier is in green there, and the groundwater flow happens to be this from the upper left to the lower right. There's a higher concentrations here. We had total CBOCs up to 10 milligrams per liter. And as we did in the first site, we did add a little bit of HRC upgradient on this as well, although the iron concentrations were much higher. It's the primary reduction mechanism. As the first site, we also have a monitoring well within the barrier and one downgradient as well. So the design verification that took place using the passive flux meters, and from that we were able to calculate, the Darcy velocity of the groundwater and what the concentration of PC in the water. We can also calculate the flux. Use this in our design model, try to make sure that we get this right the first time. So it was done by RRS. This is a site in the Midwest. Once again, we're trying to do a combination here of primarily chemical reduction, but we're certainly not afraid to let bio do its job as well. And you can see they're doing this on actually a sidewalk in the Midwest. So the results, this is the results within the PRB. And one thing that you should probably recognize is that the cis axis on the right is greater concentrations than the concentrations of the other compounds, which are on the left axis. If you look at it, the cis started off at about 9,000 ppb, and the TCE, although the plot looks like they're the same, it's actually about 1,200. Just put them on the same plot, and it kind of gives you an optical illusion of being similar concentrations, but they're obviously not. But as we've seen in the prior work, first monitoring period, there was a reduction. By the second monitoring period, about a month later, we had non-detect for all our contaminants within the barrier, with significant increases once again in dissolved and ethane, which once again suggests that we're actually seeing degradation here and not just sorption. So within the direct area of influence, not all that surprising, but it's still good results. Downgradient's a little bit more interesting. As I mentioned earlier, to get a response down, you actually have to have water pass through the barrier and take some time to get down to the downgradient monitoring well. And once again, we had decent reductions so far. CIS has been kind of a linear trend. Started off at 56,000 ppb, and probably about a 70% reduction to date. TC is basically gone or non-detect. The vinyl has gone down considerably as well. What I think is interesting here is that we're actually not seeing an increase in vinyl. If you had primarily biological degradation, you'd see cis degrade to ethane and ethane through vinyl. You probably see a little bit of a spike there. And even though we have a very high concentration initially of cis here, we're not seeing that, which is super good, because as most of you know, that a lot of the regulators are more concerned about vinyl for vein intrusion, et cetera, than they actually are for the parents. So that's a really, really favorable, and we're going to keep on monitoring this job, and hopefully we'll keep on getting good results. So that's the summary of the technology, and you know, some sites that we've applied this on. And this is this three. I'd guess that in the last 2 years, it's probably been used on dozens, maybe 30 different sites, and we're installing new remediation approaches, you know, basically several a month. As you'd expect, you know, colloidal carbon, great sorbent. As you know, it works great in above ground tanks, but when we can get the particle size down, can inject it, apply it uniformly, and, you know, get a basically near immediate, you know, 3 order of magnitude contaminant reduction within the injected barriers. You can see the downgradient effects are realized with groundwater flow. There's a delayed response there, but that's to be expected because the downgradient wells don't have a direct influence generally of your injected materials. And, you know, we've seen improved time. Colloidal iron provides a degradation mechanism that's with colloidal carbon to make the process complete and degrade with rapid kinetics and water. So that's it. If anybody has any questions, you can contact your manager for Regenesis, or you can just look me up and contact me directly. My email is jfreim@regenesis.com. We'll be happy to your side through the technical services team, and hopefully we can come up with some solutions that will help you bring your sites to closure. All right, thank you very much.